Unix 3.8, we have a series of questions, and we will be focused on tangent functions. Now, this is from the AP curriculum, so if you are struggling with this, you know where to find those section reviews with AP curriculum on my website. Let's get started with this problem. The function f is given by the following equation, which the following gives a vertical asymptote. So we know there's a vertical asymptote when the denominator of a fraction equals 0. So let's just think, first of all, let's think about y equals the tangent of x. Now, y equals the tangent of x. Well, tangent is equivalent to the sine of x over the cosine of x. So we want to know, where is the cosine equal to 0? And so let's think of our unit circle. And let's think of this in a couple different ways that may help you to better understand it. Let me grab a different color here. Color and marker pen. Okay, first of all, where is the cosine equal to 0? So let's just think of these major points here. At this point, we're at 1, 0. This is at 0, 1. On the unit circle, negative 1, 0. And 0, negative 1. The cosine, which is the first term in this ordered pair, is 0 both at pi over 2, and it's also 0 at 3 pi over 2. So the first time we experience where the cosine is equal to 0 on the unit circle is at pi over 2, and then you're going to shift this 180 degrees, which is equivalent to pi. So every time we move a distance of pi around the unit circle, we hit another spot on the unit circle in which the cosine is equal to 0. So keep that in mind. Now, how can we write that? So we want to be able to share that places in which we can find a vertical asymptote for this function. Now, we'll get to this part and how does this part influence it in just a second. But we know that at pi over 2, we have a problem because the cosine is 0, and that would make this function have a vertical asymptote. And then if we rotate it a distance of pi, every time we rotate a distance of pi as we go around the unit circle, we also experience the exact same problem. So we can say every time we rotate a distance of pi around the unit circle. So whether we rotate it 3 times, 1, 2, 3, we still have that problem. The cosine is equal to 0. So that's how we're able to achieve this answer. Now, what does this do? That's just kind of there as a distractor. So we think of our general function here. We're right here, and our general function looks like this, right? And we've already said that we have vertical asymptotes at pi over 2, and this would be at negative pi over 2, right? And then it repeats itself again, so it's like this. So if I add pi to this, this would be at 3 pi over 2, right? And I just keep adding pi's. So what does this do to it? This just says that this point, which is an inflection point, by the way, see how this is concave down, boop, concave up. You see how it switches there? This inflection point is moved up 1. In fact, all of these points are rotated up 1. I personally don't like it written in this form. It's almost there to distract you. I like it like this, when that vertical shift is up 1, and you're free to rewrite it. So that's what this means, that we're shifting up 1, but that doesn't change our vertical asymptotes. Now this 2 says that all these points are going to be stretched by a factor of 2. So it just means that this basic shape that we see, that is going to lie in between these vertical asymptotes, it's just going to be stretched at a faster rate. So it's going to rise up and it's going to fall at a faster rate. That's it. It doesn't change the asymptotes at all. It's just there as a distractor. This is our correct way for us to distinguish where we can find vertical asymptotes for this function. In fact, for all tangent functions. For all tangent functions where we have 1x behind the tangent.